So let's start with exercise 1.1, the first sum. The first sum is determine whether each of the following relations are reflexive, symmetric and transitive. So they are giving you 5 sums, 5 subdivisions. So the first one is relation R in the set A is equal to 1, 2, 3 until 14. So they have given you the value of set A, that is 1, 2, 3 until 14, and the relation R is defined on A such that 3x minus y is equal to 0. So the condition they are giving for relation is 3x minus y should be equal to 0. That is the condition for relation. Okay. Now they are asking you to check if this relation is reflexive, symmetric and transitive. So from the condition that is given, you can find the values of R, right? So what will be the values? What are the values of R? Let's take x to be 1. If x is 1, 3 ones are 3, 3 minus, now what should be the value of y so that 3 minus y becomes 0? Y should be 3, isn't it? So if x is 1, 3 ones are 3, 3 minus 3 will be 0. So y will be 3. Now if x is 2, 2 3s are 6, 6 minus 6 will be 0. So if x is 2, y becomes 6. If x is 3, 3 3s are 9, 9 minus 9 will be 0. If x is 4, 4 3s are 12, 12 minus 12 will be 0. If x is 5, what happens? 5 3s are 15, 15 minus 15 will be equal to 0, but 15 is not there in set A, so we stop right here. There are no more values for R. Okay, now we have found the values of R. Let's start with checking for reflexive. Okay, let's start with reflexive. Check for reflexive. Okay. So what is the rule? What is the rule for reflexive? For every element A belonging to set A, ordered pair of the form A comma A should belong to R. So this is a general rule for a relation to be reflexive. You have to check for every element in A, and if every element has an ordered pair such as A comma A in the relation, then we can say the relation is reflexive. So let's start with the first element. Start with 1. For 1, do we have 1 comma 1 in the relation? Do we have A comma A? Do we have 1 comma 1 in the relation? The answer is no. There is no 1 comma 1 in R. So even if one element doesn't satisfy this condition, we can straight away say this relation is not reflexive. Okay. For element 1 belonging to A, for element 1 belonging to A, 1 comma 1 is not in the relation. Okay. Therefore, the relation is not reflexive. Okay, if 1 comma 1 is there, we will go on checking for 2. We will check for 2 comma 2. If 2 comma 2 is there, we will go on checking for 3 comma 3. So likewise, but since the first element itself did not satisfy the condition, we very well said, since for 1 belonging to A, 1 comma 1 is not there in the relation, this relation is not reflexive. Okay. Now let's go on checking for symmetric. Reflexive is done, so we will now check for symmetric. So, for a relation to be symmetric, what is the rule here? What is the common rule? If A comma B belongs to R, then B comma A should belong to R. So this is the general rule for relation to be symmetric. If A comma B belongs to R, then we have to check for B comma A. If B comma A is also in R, for every A comma B in R, B comma A should be in R. In that case, that relation will be a symmetric relation. So let's start with the first pair. start with the first pair. Here 1 is A and B, 3 is B. Okay. So for 1, 3 in the relation, do we have 3, 1? Do we have 3, 1? No, there is no 3, 1 in the relation. So we can say this relation is not symmetric. Okay. For 1, 3 belonging to R, okay, 3, 1 is not present in R. So thus we can conclude that the relation is not symmetric. Okay. Now let's check for transitive. We are done with reflexive and symmetric. Now we will check for transitive. So what is the rule for relation to be transitive? What is the rule? If A, B and B, C belong to R, if A, B and B, C belong to R, then A, C should belong to R. So this is the rule for any relation to be transitive. So we have to check for A, B and B, C in the relation. If they are there, if ordered pairs of this form, if they are there in the relation, then we will go on checking for A, C. Okay. Here, let's check this pair. Okay. 1, 3. This is A and this is B. C. And this will be B and this will be C, right? So A, B, B, C. We got a pair. Okay. So now because A, B and B, C is there in the relation, we will check for A, C now. What is A, C? 1, 9. Do we have 1, 9? No. There is no 1, 9 in the relation. So we can say this relation is also not transitive. So how do we write? For 1, 3 and 3, 9 in the relation. Okay. 1, 9 is not there in the relation. For 1, 3 and 3, 9 in the relation, 1, 9 is not present. Therefore, the relation is not transitive. Okay. So this relation is neither reflexive nor symmetric and not transitive. It has failed all three conditions. Okay. So now let's move on to the second sum. That is, relation R in the set N of natural numbers defined as R is equal to x, y such that y equals x plus 5 and x is less than 4. So they are given that set N is capital N is nothing but set of all natural numbers. That is, starts from 1, 2, 3, goes on. That's an infinite set. And the relation is defined as x, y such that y equals x plus 5 and x is less than 4. So they are telling you that the values of x should be less than 4. So from this set, you can say that the values of x are going to be 1, 2 and 3. And the value of y can be found out using this equation. So now, what are the values of R? If x is 1, what is going to be y? Y will be x plus 5. That is 1 plus 5 equals 6. Right? If x is 2, y will be 2 plus 5, that is 7. If x is 3, y will be 3 plus 5, that is 8. If, that's it, right? Sorry. So, because x is less than 4, we stop right here. So, we close the bracket. So, these are the values of R. Now, we start with the first. That is, let's start checking for reflexive, then symmetric, then transitive. The first one is reflexive. Check for reflexive. What is the rule here? We know that the rule is for every A belonging to set A, order pair of the form A comma A should belong to R. So this is the rule for any relation to be reflexive. So let's check in the relation if we have. For 1, do we have 1 comma 1? No. So that itself proves that this relation is not reflexive. Just check for any one element. If that element does not satisfy, you straight away say this is not reflexive. So for 1 belonging to n, 1 comma 1 is not present in R. Okay. Therefore, we can conclude that the relation is not reflexive. Okay. Now let's check for symmetric. Check for symmetric. For relation to be symmetric, what is the rule? The rule is if A comma B belongs to R, then B comma A should belong to R. So this is the rule for relation to be symmetric. So let's take the first order pair. For 1 comma 6, do we have 6 comma 1 in the relation? No. So this proves this relation is also not symmetric. For 1 comma 6 belonging to R, 6 comma 1 is not present in R. So we conclude that the relation is not symmetric. Okay. So this relation is not symmetric. Now let's check for transitive. Check for transitive. So what is the rule for relation to be transitive? The rule is if A comma B and B comma C belong to R, if A comma B and B comma C belong to R, then A comma C should belong to R. Right? This is the rule for any relation to be transitive. Okay. Now let's check in this relation if there are ordered pairs such as A comma B and B comma C. You have 1 comma 6. If that is A comma B, do you have any 6 comma something? No, B comma C is there. For 2 comma 7, do you have 7 comma something? No. For 3 comma 8, do you have 8 comma something? No. So in this relation, we don't have any ordered pairs such as A comma B and B comma C. In such a case where there are no ordered pairs such as A comma B and B comma C in the relation, such a relation is assumed to be transitive. So that is the rule. If you have any ordered pairs such as A comma B and B comma C, for example, if you have 1 comma 6, you have 1 comma 6 here. If you have 6 comma 3 or 6 comma 4 or even 6 comma 1, then it means we have A comma B and B comma C in the relation. We have to check for A comma C in that case. If A comma C is there, you will say it is transitive. If it is not there, you will say not transitive. But here, there is no pair such as A comma B and B comma C in the relation. So we will say, assume this relation to be transitive. Okay, how do we write? Since no ordered pairs such as A comma B and B comma C are present in the relation which is assumed to be transitive. Okay. The conclusion is, therefore, the relation is transitive. Okay, done, understood? So, what is the final answer for this sum? This relation is not reflexive, not symmetric, but it is transitive. So next is exercise 1.1, third sum. Okay. The third sum is relation R in the set A equals 1, 2, 3, 4, 5, 6. So they are given set A to be 1, 2, 3, 4, 5 and 6. And the relation is defined as R is equal to x comma y such that y is divisible by x. So the condition for relation is y should be divisible by x, meaning y has to be a multiple of x. In other words, x will divide y into some number of equal parts. Okay. So from this relation that is given, let's find the values of R. Okay. We have to check every ordered pair. Only then we will be able to find what pairs come inside the relation. So let's start with 1. So 1, take the first element and start checking for each pairs having x to be 1. So start with 1 comma 1. Okay. For 1 comma 1, 1 is divisible by 1. So obviously 1 comma 1 falls in the relation. Check for 1 comma 2, which means 1 comma 2. Here 1 will be x and 2 will be y. We have to check if y is divisible by x, meaning we have to check if 2 is divisible by 1. Of course, any number will be divisible by 1. You can say 1 comma 2 comes in the relation. Then check for 1 comma 3. Of course, 1 comma 3 same. 3 is divisible by 1. 4 is divisible by 1. 5 is divisible by 1. And 6 is divisible by 1. Get it? Now, let's move on to the next element. That is 2. So, for 2 comma 1, in case of 2 comma 1, 2 will be x, 1 will be y. We have to check if 1 is divisible by 2. If 1 is divisible by 2, is it divisible by 2? No. 1 is not divisible by 2. So, 2 comma 1 will not come in the relation. Then 2 comma 2. Any number is divisible by the same number. So, okay. 2 is divisible by 2. So, 2 comma 2 comes in the relation. Then check for 2 comma 3. 3 is not divisible by 2. So, no need. 2 comma 4. 4 is divisible by 2. 2s are 4, right? 4 is divisible by 2. So, 2 comma 4 should write. 2 comma 5. 5 is not divisible by 2. 2 comma 6. Of course, 6 is divisible by 2. Then, go to 3. 3 comma 1. No. 1 is not divisible by 3. 3 comma 2. No. 2 is not divisible by 3. 3 comma 3. Yes. Any number is divisible by the same number. 3 comma 4. No. Because 4 is not divisible by 3. 3 comma 5. No. 3 comma 6. Yes. Because 6 is divisible by 3. Then check for 4. 4 comma 1. No. Because 1 is not divisible by 4. 4 comma 2. No. Because 2 is not divisible by 4. 4 comma 3. No. 4 comma 4 will come. Okay. 4 comma 5. No. 5 is not divisible by 4. 4 comma 6 also no. Then go to 5. Again 5 comma 1 no. 5 comma 2 no. 5 comma 3 no. 5 comma 4 no. But 5 comma 5 will come. Okay. Then move on to 6. 6 comma 1 no. Everything no. 6 comma 2 no. 6 comma 3 no. 6 comma 1. Only 6 comma 6 will come. So that's it. So now we have found all the values of R. Now let's check for reflexive. Okay. Reflexive. For a relation to be reflexive, what is the rule? You know that for every element A belonging to A, order pair of the form A comma A should belong to R. For every element A belonging to A, order pair of the form A comma A should belong to R. This is the general rule for any relation to be reflexive. Now looking at the values of R, okay, checking for every element in A, that is for all elements in A, you have to check if A comma A is there in the relation R. So for 1, we have 1 comma 1. For 2, we have 2 comma 2. 3, we have 3 comma 3. For 4, we have 4 comma 4. For 5, we have 5 comma 5. And for 6, we have 6 comma 6. So now that we have all, for every element in A, there is an ordered pair in the relation of the form A comma A. So this proves this relation is reflexive. Okay. Now, how do we write? Since 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5, and 6 comma 6 belong to R. Since these pairs belong to R, the relation is reflexive. The relation is reflexive. Okay. Now let's check for symmetry. We are done with reflexive. Now we will check for symmetry. For relation to be symmetric, what is the rule? The general rule is if A comma B belongs to R, then order pair of the form B comma A should belong to R. So this is the rule for reflexivity. For symmetry. Okay. So if A comma B belongs to R, then B comma A should belong to R. You know the values of R. Let's start checking. For 1 comma 1, this is A and this is B. Of course, B comma A is there, which is also going to be 1 comma 1, right? So we will leave that. Take the next pair, that is 1 comma 2. This is 1 is A and 2 is B. For 1 comma 2, do we have B comma A? Do we have 2 comma 1 in the relation? As we see, there is no 2 comma 1 in the relation. So this relation is not symmetric. Even if one pair is proved to be not satisfying this relation, this condition, then we can very well say the entire relation is not symmetric. You don't have to go on checking it. Okay, you will stop right here. So for 1 comma 2 belonging to R, 2 comma 1 is not present in R. This is how you write. For 1 comma 2 belonging to R, 2 comma 1 is not present in R. So this relation is not symmetric. Therefore, the relation is not symmetric. Okay. Now let's check for transitive. We are done with reflexive and symmetric. Now we will check for transitive. What is the general rule for any relation to be transitive? The rule is such that if A comma B and B comma C belong to R, if A comma B and B comma C belong to R, then A comma C should belong to R. Should belong to R. This is the rule, right? Now, for this sum, we will take a different number. Now, I will start by saying if x comma y belongs to R. Here I am talking in terms of x and y because that is how it is given in the sum. The general rule is A comma B. But since it is x and y in the sum, we will start saying x and y itself. So if x comma y belongs to R, what does it imply? It implies that as per the sum, as per the relation given in the sum, it implies that y is divisible by x, right? That's what it implies. Y is divisible by x, right? Now, from this, what does this mean? That y is divisible by x? It means that y is equal to some number of times x. Because x divides y into some number of parts. So we can say that this y is equal to some number of times x. That's what we will write now. Let y be equal to mx, where m is any positive integer. So I am writing y is equal to m into x. What is this m? This m is any positive integer. So this means y is m times x. That is what it means, right? So now, if y comma z belong to R, if y comma z, that is b comma c, right? If y comma z belongs to R, it implies that z is divisible by y. It implies that z is divisible by y. Now, from this, you will write let z be equals n y. Let z be equals n times y. Because z is divisible by y, we are writing that as z is equal to n times y. What is n here? Where n is any positive integer. Again, any positive integer. Okay, now we got two equations. We need to find the relationship between x and z. We don't need y. Y has to be taken out. What can we do here? Look at this equation. Z equals n y. Instead of y, we can substitute mx, right? Because y is equal to mx, we can substitute mx in place of y. So this equation will become what? Z is equal to, therefore z is equal to m n x. Sorry, m n x. So this is how it will become. Z is equal to n into mx. That is m n x. So what does this mean? Z is m n times x. That is what it means. That is, m is a positive integer. N is also a positive integer. Multiply, you will get a positive integer. Right? So z is equal to m n times x. Which means, what does it mean? Z is divisible by x. It means z is divisible by x, which implies x comma z belongs to R. This condition is satisfied. This, we have found that z is divisible by x, so we can very well say x comma z belongs to R. If x comma z belongs to R, A comma C, if x comma z belongs to R, x comma y belongs to R, y comma z belongs to R, and x comma z also belongs to R. So this relation is, therefore the relation is transitive. You can say the relation is transitive. I have less space, so I am writing it here and there. So I hope you are clear with this. So we are finally checked for three conditions. For reflexive, this relation is reflexive. This relation is not symmetric, but it is transitive. Okay. Exercise 1.1, fourth sum. The first sum is relation R intersect Z of all integers. So it is given that Z is equal to set of all integers, and the relation R is defined on Z such that x minus y is an integer. So the sum is, they have given you the set Z, which is going to be a set of all integers, and the relation R is defined on Z such that x minus y is an integer. We are asked to find if this relation is reflexive or symmetric or transitive. So we will first start with reflexive. Check for reflexive. Check for reflexive. What is the rule for reflexive? The rule is, for every A belonging to A, set A, order pair of the form A comma A should belong to R. So this is a rule for a relation to be reflexive. Now, in this case, let us assume that if x comma x belongs to R, we will talk in terms of x and y. Okay, if x comma x belongs to R, belongs to the relation, okay, then what does it imply? It implies that x minus x is an integer, right? If I am going to tell that x comma x is in the relation, if I am telling you that x comma x is in the relation, I can say it is in the relation only if x minus x is an integer, right? So this implies x minus x is an integer. Now let's see what is x minus x. Okay, x minus x is equal to 0, right? X minus x is equal to 0. Since 0 is an integer, we can confirm that x comma x belongs to R. X comma x belongs to R. Therefore, the relation is reflexive. So, how did we start? We started by telling that if x comma x belongs to R. I am assuming that x comma x is in the relation. If it is in the relation, what is the rule? X minus y should be an integer. In this case, x minus x. So I found that x minus x, it is 0. X minus x is found out to be 0 because 0 is an integer. Since 0 is an integer, this condition is satisfied. That x minus y is an integer condition is satisfied. Therefore, x comma x will belong to the relation. Therefore, this relation is reflexive. Okay. Now let's check for symmetry. What is the rule for symmetry? You know the rule is if A comma B belongs to R, then B comma A should belong to R. So this is the rule for any relation to be symmetric. Right? So, if A comma B belongs to R, then B comma A should belong to R. That is the rule. Okay. Now, in this case, let me assume that if x comma y belongs to R, if x comma y belongs to R, it implies that, what does it imply? It implies that x minus y is an integer. It implies that x minus y is an integer. Okay. Now, let x minus y be equals, say, m, where m is an integer. Where m is any integer. Okay. I am assuming that integer to be m. Okay. Now, how can I write this equation? I can write this as y minus x is equal to minus m. X minus y is equal to m. So, we are changing sides. It becomes y minus x will be equal to minus m. Now, minus m is also an integer. Since minus m is also an integer, here we have y minus x. It means y comma x belongs to R. Therefore, y comma x belongs to R. Therefore, the relation is symmetric. You understand, right? Relation is symmetric. So we start off like how? If x comma y belongs to R, if it is in the relation, it implies that x minus y is an integer. Okay. Now I am taking x minus y to be m, where m is any integer. Okay. We can write this equation as y minus x is equal to minus m. Minus m is also an integer. Okay. So since y minus x is also an integer, we can say y comma x belongs to the relation. Therefore, this relation is symmetric. Now let's check for transitive. Check for transitive. What is the rule for a relation to be transitive? The rule is if a comma b and b comma c belong to R, if a comma b and b comma c belong to R, then a comma c should belong to R. Should belong to R. So this is the rule for any relation to be transitive, right? Now, how do we prove that this relation is transitive? Let's start by saying if x comma y belongs to R, if x comma y belongs to R, okay, it implies that x minus y is an integer, right? If I am telling you that x comma y belongs to the relation, then I can say so only if x minus y is an integer, right? Now, here we will take, let x minus y be equals m, where m is any integer. Where m is any integer. We are assuming x minus y to be m. Now, if y comma z belongs to R, if y comma z, if this pair is in the relation, then what does it imply? It implies that y minus z is an integer. It implies that y minus z is an integer. Now, let's take let y minus z be equals n, where n is any integer. Where n is any integer. Okay, now we have two equations. What we will do now is we will add these two equations. Why do we add? Now we have to find a relation between x and z. We need to cut off y from this. So, while we add, what do we get? X minus y plus y minus z equals what? M plus n. Right? When you add these two equations, you get x minus y plus y minus z equals m plus n. Now we can strike off. Plus y minus y gets strike off. So we get x minus z equals m plus n. What is m plus n? M plus n is also an integer. M is an integer, n is an integer. You add those two, you will still get an integer. Okay. Since m plus n is also an integer, what we can say? X comma z belongs to R. X comma z belongs to R. Therefore, the relation is transitive. So, how did we start? We started off by writing if x comma y belongs to R, then it implies that x minus y is an integer. We assumed x minus y to be m, where m is any integer. If y comma z belongs to R, then y minus z is an integer. Then we assume y minus z to be n, where n is an integer. Then we add these two equations. When we add, we get x minus z is equal to m plus n. M plus n is also an integer. So x comma z will belong to the relation R. Therefore, this relation is transitive. So what is the final answer that we get? For this sum, this relation is reflexive, it is symmetric, and it is transitive. Okay, let's move on to exercise 1.1, fifth sum. This fifth sum again has 5 subdivisions. So they are given you that A is nothing but the set of human beings in a town at a particular time. Set A is nothing but all human beings in a town at a particular time. That is set A. Okay. It is a bunch of people put together in set A. Okay. And the relation is defined on A such that X and Y work at the same place. So this relation is defined such that two people, X and Y, should work at the same place. Only if they work at the same place, they will fall in the relation. So this is a very simple sum, a logical sum, and it's very simple. There's no way we will make a mistake with this sum. Okay. Let's start. Okay. So we are asked to check if this relation is reflexive, symmetric, and transitive. You will start with checking for reflexive. Check for reflexive. Now we know the general rule for a relation to be reflexive is that, what does the rule state? For every element A belonging to set A, order pair of the form A, A should belong to R. So for every element A in A, order pair of the form A, A should be in the relation. Okay. Now, let me assume that if X, X belongs to R, I am just assuming that X, X, this pair, that is this identical pair, that is X, X, belongs to R. I am assuming that, okay. Now, what does this imply? This implies that X and X work at the same place. So this implies that X and X work at the same place. Is this statement true or false? Of course, X and X are the same person, right? They are the same persons, so obviously they will be working at the same place, right? So this statement is true. The above statement is true. The above statement is true. Now that X and X work at the same place, now that X and X satisfy this relation, we can say therefore X, X belongs to R. The relation is reflexive. Very simple thinking. X and X are the same persons and they will obviously be working at the same place. So this relation is reflexive. Now let's check for symmetry. Check for symmetry. What is the rule for a relation to be symmetric? The rule is if A, B belongs to R, then B, A should belong to R. So this is the rule for any relation to be symmetric. Now let's start by assuming that if X, Y belong to R. If X, Y, if I am telling you that X, Y is in R, what does that imply? It implies that X and Y work at the same place. Right? It implies that X and Y work at the same place. Okay. Now, then what does this imply? This implies that Y and X work at the same place. So if X and Y work at the same place, then Obviously, if x and y work at the same place, then y and x should also be working at the same place. If y and x work at the same place, what does it mean? Y comma x belongs to R. This implies y comma x belongs to R. Therefore, the relation is symmetric. So, we started by assuming that if x comma y belongs to R, then it means x and y work at the same place. If I am telling you that x and y work at the same place, then it obviously means that y and x should also be working at the same place. If y and x work at the same place, we can say y comma x belongs to R. Therefore, this relation is symmetric. Now, let's check for transitive. Check for transitive. So, what is the rule for a relation to be transitive? The general rule is if A comma B and B comma C belong to R, then what is it? A comma C should also belong to R. So this is the rule for a relation to be transitive, right? Okay. Now, let's start by saying if x comma y belongs to R, if x comma y belongs to R, what does it imply? It implies that x and y work at the same place. If x comma y belongs to R, it means x and y satisfy the condition for relation. It means x and y will work at the same place. Now, if y comma z belongs to R, if y comma z belongs to R, what does it imply? It implies that y and z work at the same place, right? If y comma z belongs to R, it means y and z satisfy the condition for the relation, that is, y and z will work at the same place. Okay. Now, from these two statements, what can we say? X and y work at the same place, y and z work at the same place, y is common in both. So, this means that x and z will also be working at the same place. Say, for example, x and y work in a supermarket. Okay. Now, I am saying y and z also work at the same place, which means we know where y works. If y works in supermarket, then z will also be working in the same supermarket. So, all three people, x, y and z, they all three will be working in the same supermarket only. So, this implies that, therefore, this implies that x and z work at the same place. This implies x and z work at the same place. Therefore, x comma z belongs to the relation. Therefore, the relation is transitive. How will we start? We started by assuming if x comma y belongs to R, then what does it mean? X and y will satisfy the relation, that is, x and y will work at the same place. Then, if y comma z belongs to R, then that means y and z will satisfy the relation, that is, y and z will work at the same place. Now we have two statements saying x and y work at the same place, y and z work at the same place. This implies that x and z should also be working at the same place. If x and z work at the same place, it means x comma z belongs to the relation. Therefore, x comma y is in R, y comma z is in R. If x comma z is also in R, then this relation is transitive. Okay? Exercise 1.1 with some subdivision B. Now, say B is the same. Human beings in a town at a particular time. The relation changes. What is the relation here? it is defined on A such that x and y live in the same locality. They are saying x and y live in the same locality. Okay, so let's start. Let's start by checking for reflexive. Check for reflexive. What is the general rule for any relation to be reflexive? The rule states that for every A belonging to A, outer pair of the form A comma A should belong to the relation, that is R. Should belong to R. This is the condition for a relation to be reflexive. Now, let me assume that if x comma x belongs to R, if x comma x belongs to R, it implies that, what does it imply? It implies that x and x live in the same locality. If x comma x is inside the relation, it means it will satisfy the condition for the relation. What is the condition for the relation? X and x live in the same locality. It means x and x live in the same locality. Now, is this statement true or false? It is true because x and x are nothing but the same persons. So, two same persons will obviously be living in the same locality. They can't be in different places, right? So, the above statement is true. The above statement is true. Therefore, the relation is reflexive. Okay. Understood? Okay. Now let's check for symmetry. Check for symmetry. Again, this is going to be very simple, very easy. The rule for symmetry is if A comma B belongs to R, then B comma A should belong to R. This is the rule for any relation to be symmetric. Now, let me say if x comma y belongs to R, I am assuming that x and y are in the relation, which means x and y will satisfy the condition for relation. So this implies x and y live in the same locality. Now, if x and y live in the same locality, what can we say? This again implies that y and x live in the same locality. Okay, there is no change. If x and y live in the same place, then obviously y and x should be living in the same locality. So what does this imply now? Therefore, y comma x belongs to R. From this we can say y comma x belongs to R. Therefore, this relation is symmetric. Okay, understood, right? Now let's check for transitive. Let's check for transitive. Again, this is also very simple. What is the rule for transitive? The rule is if A comma B and B comma C belong to R, then A comma C should belong to R. So this is the rule for any relation to be proved to be transitive, right? So now let's start. We will again start by assuming that if x comma y belongs to R, what does it imply? If I am telling that x comma y is in the relation, then it implies that x and y will satisfy the condition for the relation, which is x and y live in the same locality. This x and y live in the same locality. Understood? Now, if y comma z belongs to R, if y comma z belongs to R, then what does it imply? It implies that y and z live in the same locality. Right? So, I am taking x comma y to be in the relation, then it means that x and y live in the same locality, and I am assuming y comma z to be in the relation, which means y and z live in the same locality. Now, from these two statements, what can we say? X and y live in the same place, y and z live in the same place. So, this we have a common element here. Y is common. So, of course, obviously, x and z will live in the same locality. So, this implies that x and z live in the same locality. Therefore, x comma z what? Belongs to what? Belongs to the relation. Therefore, the relation is transitive. So, how did we start? We started by assuming x comma y to be in the relation. So, this implied that x and y live in the same locality. Then y comma z, if I take it to be in the relation, it implied that y and z live in the same locality. Now, from these two statements, we can say that take y is common. So, we can say that x and z, of course, live in the same locality. Therefore, x comma z belongs to the relation R, and this relation is transitive. Now, some find subdivision C. A is the same, set of human beings in a term at a particular time. Okay. Now, the relation R defined on A is such that x is exactly 7 centimeters taller than y. So, the condition for relation is x should be 7 centimeters taller than y. Now, we asked to find if this relation is reflexive, symmetric, or transitive. Let's start with reflexive. Check for reflexive. Okay. Now, you know the rule, right? The rule is for every A belonging to A, ordered pair of the form A comma A should belong to R. This is the rule for a relation to be reflexive. Now, if we start by if x comma x belongs to R, if I am telling that x comma x is in the relation, then it will mean that x comma x should satisfy the condition for the relation. So let us check if this pair does satisfy the condition. Okay, let us check now. If x comma x belongs to R, then x should be what? X should be 7 centimeters taller than x. Here x is y. Right? Then x should be 7 centimeters taller than x. Is this possible? Can some person be 7 centimeters taller than the same person? No person can be taller than himself, right? So, the above statement is false. The above statement is false, which means therefore x comma x will not belong to the relation. Therefore, the relation is not reflexive. So, we assume the x comma x to be in the relation. If x comma x belongs to the relation, then it will mean that x is 7 centimeters taller than x. Okay. But that is not possible because some person cannot be 7 centimeters taller than the same person himself. Right? So, the above statement is false. Therefore, x comma x does not belong to the relation, therefore the relation is not reflexive. Okay. Now let's check for symmetry. Reflexive is done. Let's check for symmetry. What is the rule for a relation to be symmetric? The rule states that if A comma B belongs to R, then B comma A should belong to R. This is the rule for a relation to be symmetric. Okay, now if let us assume that if x comma y belongs to R, okay, if x comma y belongs to R, what does it imply? It implies that x is 7 centimeters taller than y. Okay, it implies that x is 7 centimeters taller than y according to the condition for the relation. Now, if y comma x belongs to R, if I am telling you that y comma x belongs to R, what does it imply? It implies that y is 7 centimeters taller than x. So if x comma y belongs to R, then it will mean that x is 7 centimeters taller than y. But if y comma x belongs to R, it will mean that y is 7 centimeters taller than x. Is this possible? These two statements, they are contradictory. If x is taller than y, 7 centimeters, then y will be 7 centimeters shorter than y. Y can't be taller than y. The above statements are contradictory. The above statements are contradictory. Okay. They are clashing with each other because y is 7 centimeters shorter than x. Therefore, y comma x will not belong to the relation. Okay. Therefore, the relation is not symmetric. The relation is not symmetric. Okay. Now, if x comma y belongs to R, this is how we started, right? If x comma y belongs to R, it means that x is 7 centimeters taller than y. Now, if I am telling you that y comma x also belongs to R, what does it mean? It implies that y is 7 centimeters taller than x. Is that possible? It is not possible. So we say that the above statements are contradictory. They are not going in sync with each other. They are clashing. So because these statements are, the above statements are contradictory. Why? Because y is actually 7 centimeters shorter than x. As per this relation, y will be 7 centimeters shorter than x. Therefore, y comma x will not belong to R. Therefore, this relation is not symmetric. Okay. Now let's check for transitive. Check for transitive. What is the rule for a relation to be transitive? You all know very well, right? So the rule is if A comma B and B comma C belong to R, then order pair of the form A comma C should belong to R. So this is the rule for any relation to be proved to be transitive, right? So let's start this one. We will start with if. Okay, if x comma y belongs to R. If x comma y belongs to R, what does it imply? It implies that x is 7 centimeters taller than y. As per the relation given in the sum, it implies that x is 7 centimeters taller than y. Now, if y comma z belongs to R, if y comma z belongs to the relation R, what does it imply? It implies that y is 7 centimeters taller than z. It implies that y is 7 centimeters taller than z. So looking at these two statements, what can we say? X is 7 centimeters taller than y, okay, and y is 7 centimeters taller than z. I need to find a relation between x and z, between x and z. I need to find the relation between x and z. I don't want y. So what is the relation between x and z? We know that x is 7 centimeters taller than y and y is 7 centimeters taller than z. So x will be 7 plus 7, that is 14 centimeters taller than z. Do you understand? How? Let's do a rough diagram here. Height of x, height of y, height of z. Okay. The difference in heights between x and y is what? 7. X is 7 centimeters taller than y, right? So this difference is 7. And the difference in heights between y and z. Y is 7 centimeters taller than z. So the difference in height between y and z is 7. So now what is the difference in height between x and z? 7 plus 7, 14. So the x is actually 14 centimeters taller than z. So from the two statements, we can say that x is 14 centimeters taller than z. Therefore, what? Does this follow the relation? No. It has to be exactly 7 centimeters taller than z. So, x comma z does not belong to R. Right? Therefore, the relation is not transitive. Okay. So now we started with x comma y. If x comma y belongs to R, then x is 7 centimeters taller than y. If y comma z belongs to R, then y is 7 centimeters taller than z. Now from these two statements, we could conclude that x is 14 centimeters taller than z. Okay, which doesn't satisfy the condition for the relation. Therefore, x comma z will not be in the relation. Therefore, this relation is not transitive. Okay. Now, for some subdivision C. So, set A is the same. It is a set of human beings in a town at a particular time, and the relation is defined on A such that x is wife of y. So, this is the condition for relation. X has to be the wife of y. Okay. Now, let's start the checking for reflexive. Check for reflexive. So what is the rule for reflexive? We know. The rule for any relation to be reflexive is for every A belonging to set A, ordered pair of the form A comma A should belong to R. Okay, this is the condition for a relation to be reflexive. Now, let's start the answer. If x comma x belongs to R, if I am taking x comma x to be in the relation R, then what does it imply? It implies that x is a wife of x. It implies that x is wife of x. How is this possible? Can some person be the wife of the same person? No. Logically speaking, no. There is no chance, right? So, the above statement is false. Okay. Therefore, x comma x will not belong to the relation. Therefore, the relation is not reflexive. It is not reflexive. So we assumed x comma x to be in the relation. If x comma x is in the relation, then it has to satisfy the condition for the relation. That is, x should be wife of y. Here in this case, it is x. So x should be wife of x. Now, no person can be the wife of the same person. So this statement is false. Therefore, x comma x does not belong to the relation, and this relation is not reflexive. Okay. Now let's check for symmetry. Reflexive is done, so we will now check for symmetry. What is the rule for a relation to be symmetric? The rule states that if a comma b belongs to R, then b comma a should belong to R. Then b comma a should belong to R. So this is the rule for any relation to be symmetric. Okay. Now let's start. If x comma y belongs to R, if let's assume that x and y are in the relation. Sorry, ordered pairs x comma y are in the relation. Then what does it mean? This implies that x is wife of y. This implies that x is wife of y. Okay. This implies that x is wife of y, which means y is nothing but the whose y? Y is the husband of x. Okay. Now, if I am going to say that y comma x also belongs to the relation, if I am going to say that y comma x also belongs to the relation, what does this imply? This implies that y is the wife of x. This implies y is wife of x. Now, is this possible? Looking at these two statements, aren't they are contradictory, right? They are not syncing with each other. If x is wife of y, then how come y be the wife of x? Because y is the husband of x. So this husband y cannot be the wife of x. Right? You get it right? So, what can you say? The above statements are contradictory. The above statements are contradictory. Why? Why so? Because y is not wife of x, or y cannot be the wife of x. Because y cannot be the wife of x. Therefore, y comma x will not belong to the relation. Y comma x will not belong to the relation. Therefore, the relation is, what is it? The relation is not symmetric. Therefore, the relation is not symmetric. So, we started by saying if x comma y belongs to R, we assumed x comma y to be belonging in the relation. In that case, it will satisfy the condition for the relation, that is, x is wife of y. Then, if y comma x also belongs to R, then what does it imply? It implies that y is the wife of x. Now, these two statements are contradictory. They make no sense, right? Because if x is wife of y, then how can y be the wife of x? It is not possible, right? So, because y cannot be the wife of x, we can say y comma x does not belong to R, hence the relation is not symmetric. Now let's check for transitive. Reflexive and symmetric is done, so we will now check for transitive. So what is the rule for a relation to be transitive, if A comma B and B comma C belong to R. If A comma B and B comma C belong to R, then what? A comma C should also belong to R. A comma C should belong to R. This is the rule for any relation to be transitive. Now let's start with the detailed part. Okay, now if we will start by saying if x comma y belongs to R, if x comma y belongs to the relation, it implies that, what does it imply? It implies that x is wife of y, right? It implies that x is wife of y. Then if I am assuming y comma z is also in the relation, if y comma z belongs to R, then this implies that y is wife of z. Now looking at these two statements, x is wife of y, okay, but can y be the wife of z? It is not possible at all, right? Because x is wife of y, meaning it means that y is the husband of x, correct? Now this husband y cannot be the wife of z. It makes no sense at all. So ordered pair of the form y comma z is not possible in the relation. X comma y is possible, but y comma z is not possible. So what can we say? So in this case, in such a situation where ordered pairs a comma b and b comma c are not present together in the relation, we will assume that relation to be transitive. If they are present, if x comma y and y comma z are present in the relation, you will go on checking for x comma z. Okay, if you find x comma z, then that relation will be transitive. Okay. If it is not that, then it is not transitive. We know the general rule, right? If a comma b and b comma c, if ordered pairs a comma b and b comma c are not there in the relation together, if they are not there in the relation together, then that relation is assumed to be transitive. Okay, that is the rule, general basic rule, which you must remember. If a comma b and b comma c are not there in the relation together, then that relation is assumed to be transitive. So that is the same here. That here we are looking at a similar case only. A comma b is there, but b comma c is not there, right? It is not possible. So since these two are not there together, we will assume this relation to be transitive. Now how do we write? So the above statements are contradictory. These two statements, they are contradictory. The above statements are contradictory. Because why? Because y cannot be the wife of z. Y cannot be the wife of z. Now, since ordered pair y comma z does not belong to R, since ordered pair y comma z does not belong to R, now we can assume this relation to be transitive. Okay, you can write that. Therefore, y comma z does not belong to R. Since ordered pair y comma z is not present in the relation, it is assumed to be transitive. It is assumed to be transitive. Therefore, the relation is transitive. There will be a final answer. So, I hope you understood, guys. I am taking x comma y to be in the relation. This implied that x is wife of y. Now if y comma z belongs to the relation, then that implies that y is wife of z. These two statements are contradictory. Okay, it is not possible. Y cannot be the wife of z. The statements are contradictory because y cannot be the wife of z. Therefore, y comma z does not belong to the, cannot belong to the relation. Since ordered pair y comma z is not present in the relation, this relation is assumed to be transitive. Okay, therefore the relation is transitive. Okay. Now let's move on to question number 5, subdivision E. Okay, now again set A is the same, that is set of human beings in a town at a particular time, and relation R is defined on A such that X is father of Y. So they are giving a relation where X has to be the father of Y. Now let's start checking for reflexive. This is a very simple one. For reflexive, what is the rule for reflexive? For every A belonging to A, ordered pair of the form A comma A should belong to R. So this is the rule for any relation to be reflexive, right? You know this very well. Now, let me say that if x comma x belongs to R, I am assuming that the ordered pair x comma x is in the relation. In that case, it implies that, what does it imply? It implies that x is the father of y, that is x. It implies that x is father of x. Now, does this statement make any sense? It doesn't make any sense. This statement has no meaning because x cannot be the father of himself. Right? So, the above statement is incorrect. How do you write? We write that the above statement is incorrect. Okay? Therefore, x comma x, sorry, we missed a step. X is father of y. So, x cannot be the father of x. That is why this statement is incorrect. Okay. Therefore, x comma x does not belong to R. Hence, this relation is not reflexive. Therefore, this relation is not reflexive. Understood? So, if x comma x belongs to R, it implies that x is father of x itself. This statement is false, incorrect, it makes no sense. Because why? Because x cannot be the father of x himself. So, therefore, x comma x does not belong to R, and hence this relation is not reflexive. Now, let's check for symmetry. We are done with reflexive, we will move on to symmetry. So, for a relation to be symmetric, what is the rule? The rule is, you know very well, if A comma B belongs to R, then what? Then B comma A should belong to R. So, this is the rule for any relation to be symmetric. So, let's start. If x comma y belongs to R, what does this imply? I am assuming that x comma y is in the relation. This implies that x is father of y. This statement is okay. No complaints about this. Now, if I am telling y comma x also belongs to R, if I am telling that y comma x also belongs to R, then what does that imply? That implies that y is father of x. So that implies y is father of x. Now again, we are getting a contradictory statement. If x is father of y, then what is y? y is nothing but the son of x. So y cannot be the father of x. So in this case, what we will say? The above statements are contradictory. Again, same. The above statements are contradictory. The reason is because y cannot be the father of x. So that is the reason why these two statements are contradictory. So if y cannot be the father of x, therefore we can say that y comma x does not belong to R. Right? Hence, the relation is it symmetric or not? It is not symmetric. Okay, now how did we start? We started by saying if x comma y belongs to R, in that case, this pair should satisfy the condition for the relation that is x is father of y. So, if x comma y belongs to R, then x is father of y. Then, if ordered pair y comma x also belongs to R, then what does that imply? That implied that y is father of x. Now, these two statements are contradictory. Okay, that is why they are contradictory, because y cannot be the father of x. Right? Therefore, y comma x does not belong to R, and hence this relation is not symmetric. Now let's check for transitive. So we are done with reflexive and symmetric. Now we have moved on to transitive. What is the rule for transitive? If a comma b and b comma c belong to R, then a comma c should belong to R. This is the rule for any relation to be transitive. So let's start. Let's start by saying if x comma y belongs to R. If x comma y belongs to R, it implies that, what does it imply? It implies that x is father of y. Right? Understood? Now, if y comma z belongs to R, if I am telling you that y comma z, ordered by y comma z is also in the relation, then what does this imply? This implies that y is father of z. So this implies that y is father of z. Okay. Now this statement makes sense, and this statement also does make sense. Right? You agree? X is father of y, okay. Y can be the father of somebody. No issues, nah. But what is the relation between x and z? If x is father of y and y is father of z, then the relation between x and y, what is it? X, in fact, is the grandfather of z. X is nothing but grandfather of z. You understood, right? From these two statements, we can say that x is the grandfather of z. So now, what happens? We have ordered pair x comma y, we have ordered pair y comma z. But x comma z, you will check now. Now, from the above statements, we can say that x is the grandfather. X is grandfather of z. Okay. Therefore, x cannot be the father of z. X cannot be the father of z. But The condition for relation is x has to be the father of z. So what we can say? Now therefore x comma z does not belong to R. Therefore the relation is it transitive or not? Not transitive. So we started by saying if x comma y belongs to R, this implies that x is father of y. Very simple. And if y comma z belongs to R, then that implies that y is the father of z. Very simple. So these two statements, they are not contradictory. They make proper sense. Okay. Now we will move on to x comma z. From the above two statements, we can say that if x is father of y and y is father of z, then x is nothing but the grandfather of z. So in that case, x cannot be the father of z. But the relation is x has to be the father of z. So x comma z will not belong to the relation. Hence this relation is not transitive. Understood? Exercise 1.1, second sum. The second sum is show that the relation R in the set capital R of real numbers defined as R is equal to a comma b such that a is less than or equal to b square is neither reflexive nor symmetric nor transitive. So we are given set R. What is set R? It is a set of all real numbers. Okay, set R consists of all real numbers. So what are real numbers? Real numbers are nothing but whole numbers. Real numbers contain what? They contain all whole numbers, rational numbers and irrational numbers. They all put together form real numbers. So the set R is nothing but all real numbers. Then relation R. Relation R is defined on set R such that a is less than or equal to b square. The condition given for relation is a should be less than or equal to b square. Okay. For this relation, we are asked to prove that this relation is neither reflexive nor symmetric nor transitive. Okay. Now let's start checking for reflexive. Check for reflexive. What is the general rule for any relation to be reflexive? The rule is for every A belonging to set A, ordered pair of the form A comma A should belong to R. Ordered pair of the form A comma A should belong to R. So this is the general rule. We know that, right? Now let's check if this relation is reflexive. Okay. Now let's take for example, if A is 2. If A is 2, the relation how will it become? 2 should be less than or equal to 2 square. If A comma A has to be in R, has to be in the relation, then 2 should be less than or equal to 2 square. Now, what is 2 square? 4. It means 2 is less than or equal to 4. Of course, 2 is less than 4. So, the relation might seem to be satisfying. The condition might seem to be satisfying, but no. Wait. Let's take A to be 1 by 2. Of course, 1 by 2 is a real number, right? So, if this means for every A belonging to A, for every real number, for every number, every element in this set, this condition should satisfy, right? Now, let's take A to be 1 by 2. If A is 1 by 2, what will happen? Let's write it down. Let A be 1 by 2. Okay. Now, if A comma A belongs to R, if A comma A belongs to R, then what? A should be less than or equal to A squared. Right? This is what the relation should be. Now, what is A square? A square is nothing but 1 by 2 the whole square, right? Which is equal to 1 by 4. Here what happens? Is 1 by 2, is 1 by 2 less than or equal to 1 by 4? The answer is no, because 1 by 2 is greater than 1 by 4. Here 1 by 2 is greater than 1 by 4. Okay. Therefore, A comma A does not belong to R. Sorry. A comma A does not belong to R. Hence, the relation is proved to be not reflexive. So we have proved that this relation is not reflexive. How did we prove? We started with writing the rule. That is, for every A belonging to A comma A should belong to R. Then we assumed A to be 1 by 2. Okay, if A comma A belongs to R, if 1 by 2 comma 1 by 2 belongs to R, it means this condition has to be satisfied, right? So then A has to be less than or equal to A square. What is A square? We found A square to be 1 by 2 the whole square, that is 1 by 4. Here 1 by 2 is greater than 1 by 4. It is not less than or equal to 1 by 4. It is greater than 1 by 4. Therefore, A comma A will not belong to the relation. Hence, this relation is proved to be not reflexive. Understood? Okay. Now let's check for symmetry. Reflexive, we have proved it is not reflexive. Now we have to prove this is not symmetric also. So what is the rule? What is the rule for a relation to be symmetric? The rule is, if A comma B belongs to R, then order pair of the form B comma A should belong to R. So this is the rule for any relation to be proved to be symmetric, right? Now, let's take for example, if I say A is 1 and B is 2, let A be 1 and B be 2. What happens in that case? 1 is less than or equal to 2 square. 2 square is 4. So 1 is less than or equal to 4. Of course, that is true. Then, for B comma A, what happens? A becomes 2 and B becomes 1, right? I'm sorry, B, the pair reverses. So, 2 is less than or equal to 1 square. 2 is actually, for 1, 2 is less, which means 2 is less than or equal to 1. But 2 is greater than 1. Okay, so this proves this relation is not symmetric. Now, let's write it down. Let A be 1 and B be 2. 1 and 2 are real numbers. So we put A to be 1 and B to be 2. If A comma B belongs to R, then it implies that 1 is less than or equal to 2 squares. Okay, which implies 1 is less than or equal to 4. Right? Now, if this is true, right? This is true because 1 is less than 4. If B comma A belongs to R, this implies that 2 should be less than or equal to 1 square. Right? But what? 2 is greater than 1. 1 square is 1, so 2 is greater than 1. Therefore, B comma A does not belong to the relation. Hence, the relation is proved to be not symmetric. Proved to be not symmetric. Okay. Now how do we start? We started by writing the rule: if A comma B belongs to R, then B comma A should belong to R. We took A to be 1 and B to be 2. If A comma B belongs to R, then this implies that 1 is less than or equal to 2 square as per the condition for the relation. This implies that 1 is less than or equal to 4. Of course, 1 is less than 4. So this is true. Okay. Here in this case, if B comma A belongs to R, it implies that 2 should be less than or equal to 1 square, but 2 is greater than 1. Therefore, B comma A will not belong to R. Hence, the relation is proved to be not symmetric. Now, let's check for transitive. We are done with reflexive and symmetric. We will move on to checking for transitive. Okay. What is the rule for a relation to be transitive? The rule is if A comma B and B comma C belong to the relation R, then ordered pair of the form A comma C should belong to R. So this is the rule for any relation to be transitive. Okay. Now let's do some work in the rough column. Okay. So we will take three elements A, B and C. Okay. And we will take A less than equal to B squared, one column, B less than equal to C squared, another column, and A less than equal to C squared, another column. Okay. So these are 1, 2, 3, 4. Okay. Now we have divided into all. Now, if let's take A to be 1, if A is 1 and B is 2 and C is 3. Okay, these are just how to say something like trial and error methods. So we will first assume some numbers for these elements, A to be 1 and B to be 2 and C to be 3. For if A is 1 and B is 2, for A comma B in the relation, if A comma B is in the relation, then let's find if it satisfies the condition. So what happens? 1 should be less than or equal to 2 square, that is 1 is less than or equal to 4. Of course 1 is less than 4, so this is true. So A comma B is there in the relation. Now B comma C, 2 and 3. B is 2 and C is 3. So it means 2 should be less than or equal to C square, that is 2 should be less than or equal to 9. Of course 2 is less than 9. So B less than or equal to C square also true. Now A and C, 1 and 3. If A and C, if A comma C should be in the relation, then 1 should be less than or equal to 3 square. Okay, as per the condition. Of course 1 is less than 9. So even that becomes true. Now, if you take a different set of values, for these three values, it might seem that this relation is transitive, but if I take A to be 3, B to be 2, and C to be 3 by 2, if I take these three values for A, B and C, let's see what happens. So A is 3, B is 2, A is less than or equal to B square, meaning 3 is less than or equal to 2 square. So 3 is less than or equal to 4, 3 is less than 4, so this is true. Okay. So A comma B is there in the relation. Now B comma C, which means 2 is less than or equal to 3 by 2 the whole square. Okay. 2 is less than or equal to 3 by 2 the whole square. What is 3 by 2 the whole square? 9 by 4, right? 9 by 4. What is 9 by 4? 2.25. 2.25, right? Of course, 2 is less than 2.25. So B comma C is also there in the relation. For B to be 2 and C is 3 by 2, then B is less than or equal to C square is true. You understood this, right? So for B and C, 2 should be less than or equal to 3 by 2 the whole square. 3 by 2 the whole square is nothing but 9 by 4. 9 by 4 is nothing but 2.25. 2 is less than 2.25. So even that relation is true. So now we know that A comma B and B comma C are there in the relation. Let's go checking for A comma C, the final check. So if A is 3, now A is 3 and C is 3 by 2. We have to check if 3 is less than or equal to 3 by 2 the whole square. 3 is less than or equal to 3 by 2 the whole square. What is 3 by 2 the whole square? 9 by 4, that is 2.25. So this implies 3 is less than or equal to 2.25, which is false. 3 is greater than 2.25. So this is false. So finally we found for these, for if A is 3 and B is 2 and C is 3 by 2, A comma C does not belong to R. A comma B is in R, B comma C is in R, but A comma C is not there in R. So finally we can say that this relation is not transitive. For any one set of terms, if you prove that A comma C is not there in R, you can straight away say that that relation is not transitive. We need just one example to prove. Now, how do you write this? Let A be 3, B be 2 and C be 3 by 2. If A comma B belongs to R, it implies that 3 is less than or equal to 2 square, which implies 3 is less than or equal to 4. This is true. Okay, this is true. Now, if B comma C belongs to R, okay, this implies 2 is less than or equal to 3 by 2 the whole square. This implies 2 is less than or equal to 9 by 4. This implies 2 is less than or equal to 2.25. This is also true. Right. Now, if A comma C belongs to R, then it implies that 3 is less than or equal to 3 by 2 the whole square, which implies 3 is less than or equal to 9 by 4, which implies 3 is less than or equal to 2.25. But since 3 is not less than or equal to 2.25, we can say A comma C does not belong to the relation. Therefore, it is proved to be not transitive. I have very little space here, so pardon me. So how did we start? We started by saying the rule: if A comma B and B comma C belong to R, then A comma C should belong to R. We took A to be 3, B to be 2, and C to be 3 by 2. Of course, they are all real numbers. Then, if A comma B belongs to R, let's check. 3 is less than or equal to 2 square, that is 4. Of course, 3 is less than 4, so this is true. If B comma C belongs to R, then it implies that 2 should be less than or equal to 3 by 2 the whole square, that is equal to 2 is less than or equal to 9 by 4, that is 2 is less than or equal to 2.25. This is also true. Now, if A comma C should belong to R, then what does it imply? It implies that 3 is less than or equal to 3 by 2 the whole square, that is 3 is less than or equal to 9 by 4, 3 is less than or equal to 2.25. This is not true because 3 is greater than 2.25. Since 3 is not less than equal to or equal to 2.25, A comma C does not belong to R. Hence, it is proved that this relation is not transitive. So now we have final answer is we have proved this relation to be neither reflexive nor symmetric nor transitive. All three are proved. Okay. Exercise 1.1, third sum. Check whether the relation R defined in the set 1, 2, 3, 4, 5, 6 as R equals A comma B such that B equals A plus 1 is reflexive, symmetric or transitive. So they are given you a set. It has elements 1, 2, 3, 4, 5 and 6. And the relation is defined on that set such that B equals A plus 1. The condition for the relation is B must be equal to A plus 1. Now, looking at this condition, what we can do? You know the values of the elements of the set and we know the condition. We can find the values of R. So R will be equal to what? If A is 1, if A is 1, B will be A plus 1, that is 1 plus 1, that is 2. Right? If A is 2, then B will be 3, 2 plus 1, that is 3. If A is 3, then B will be 3 plus 1, that is 4. If A is 4, then B will be 4 plus 1, that is 5. If A is 5, then B will be 5 plus 1, that is 6. If A is 6, then B will be 6 plus 1, that is 7. 7 is not there in the set, so we will stop with 5, 6. So these are the values of R. Now that we have found the values of R, let's start checking for reflexive, symmetric and transitive. Starting with reflexive. Check for reflexive. What is the rule? You know the rule is, for every A belonging to set A, ordered pair of the form A comma A should belong to R. So this is the rule for any relation to be reflexive. Right? Now, looking at this relation, you know the values of R? So looking at the values of R, do we have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6? No. So, now how do we say? Since 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 and 6, 6 do not belong to R. Since these pairs do not belong to R, we can say that the relation is not reflexive. Right? So this is very simple, right? Then, moving on to symmetry. Check for symmetry. So what is the rule for a relation to be symmetric? The rule is, if A comma B belongs to R, then B comma A should belong to R. So this is the rule for any relation to be symmetric. So looking at the values of R, take the first pair 1, 2. For this first pair, do you have B comma A? Do you have 2, 1? No. So we can straight away say this relation is not symmetric. How do we write? For 1, 2 belonging to R, 2, 1 is not present in R. Hence, the relation is not symmetric. Very simple, right? Now let's check for transitive. We are done with reflexive and symmetric. We have moved on to transitive. So what is the rule for any relation to be proved to be transitive? If A comma B and B comma C belong to R, then A comma C should belong to R. This is the rule for any relation to be proved to be transitive. Again, now looking at the values of R, what can you say? 1, 2. Take 1, 2. Here this is A and this is B. Because we have 2, 3. So this is B and this is C. So this first condition is satisfied. A comma B is there, B comma C is there. Now we will check for A comma C. Do we have 1, 3 in the relation? No. Now since we do not have 1, 3 in the relation, we will say this relation is not transitive. Right? How do you write? For 1, 2 and 2, 3 belonging to R. Okay. 1, 3 does not belong to R. Therefore, the relation is not transitive. So, what is the final answer? This relation is neither reflexive nor symmetric nor transitive. Okay. Exercise 1.1, fourth sum. So, what is the fourth sum? Show that the relation R in R defined as R is equal to A comma B such that A is less than or equal to B is reflexive and transitive but not symmetric. Here, they have given you set R. Okay, the set is R, which is nothing but all real numbers, and the relation is defined on this set of all real numbers such that R is equal to A comma B such that A is less than or equal to B. The condition given for relation is A has to be less than or equal to B. So, we asked to check, sorry, asking to check. Okay, we are asked to prove that this relation is reflexive and transitive but not symmetric. How do we prove? Let's start with checking for reflexive. Checking for reflexive is first write the rule. What is the rule? For every A belonging to set A, order pair of the form A comma A should belong to R. Okay. So this is the rule for any relation to be reflexive. Now, set R is set of all real numbers. Okay. So, if, let me say, if A comma A belongs to R, if I consider that order pair of the form A comma A belongs to R, belongs to the relation R, then what does it imply? It implies that A is less than or equal to A. A is less than or equal to A. Of course, any element will be equal to the same element, right? Any number, any real number will be equal to the same real number. Agreed now? So, this is true. This is true. Therefore what? A comma A belongs to R. Hence, the relation is proved to be reflexive. Hence, the relation is proved to be reflexive. So, how did we start? We wrote the rule for every A belonging to A comma A should belong to R. Then, I took if A comma A belongs to R. If in case A comma A belongs to R, then what does that imply? It implies that A should be less than or equal to A. That is what we wrote. Because we know that A will always be equal to A, this is true. Therefore, A comma A belongs to R, and hence this relation is proved to be reflexive. Now let's check for symmetry. We have proved it is reflexive. We will now check for symmetry. What is the rule again? The rule states that if A comma B belongs to R, then order pair of the form B comma A should also belong to R. This is the rule for any relation to be symmetric. Okay. Now let me assume again, if A comma B belongs to R, I am telling that let A comma B belong to R. Then it implies that, what does it imply? It implies that A is less than or equal to B. Right? It implies that A is less than or equal to B. Now, if B comma A belongs to R, if this B comma A belongs to R, then what does that imply? That implies that B is less than or equal to A. That implies that B is less than or equal to A. Now this is not true. These two statements, they are not true. Like if A is less than or equal to B, let's say for example, if A is 2 and B is 3, then in that case, 2 is less than or equal to 3. 2 is less than 3. Therefore, 2, 3 belongs to R. Then, here, what happens? 3, 2. B, A is what? 3, 2 here. If 3, 2 belongs to R, what happens? It will mean that 3 is less than or equal to 2, but 3 is greater than. Therefore, B, A, this is not true. This is the point. This is not true. Therefore, B, A does not belong to R. Hence, the relation is not symmetric. Okay. We can also do the sum by taking an example. No harm taking an example. So, let A be 2 and B be 3, and we can give A, B belongs to R. It implies that 2 is less than or equal to 3. Now this is true. Okay. Now, checking for B, A. If B, A belongs to R, it implies that 3 is less than or equal to 2. This is false. This is false. Therefore, B, A does not belong to R. Therefore, the relation is not symmetric. It is proved to be not symmetric. So, two ways of doing. Both are correct only. Now let's check for transitive. Okay. We are done with reflexive and symmetric, and now we will check for transitive. For a relation to be transitive, what is the rule? If A, B and B, C belong to R, then A, C should belong to R. So this is the rule for any relation to be proved to be transitive. Okay. Now let's start. If A, B belongs to R, if A, B belongs to R, it implies that, what does it imply? It implies that A is less than or equal to B. Okay. Now, then, let's move to B, C. If B, C belongs to R, it implies that B is less than or equal to C. So, if A, B belongs to R, it implies A is less than or equal to B. If B, C belongs to R, it implies B is less than or equal to C. Now, from these two statements, A is less than or equal to B, B is less than or equal to C. Now, A is less than or equal to B, understand very well, and B is again going to be less than or equal to another number, which means, now what is the relation between A and C? This implies that, this itself implies that A will be less than or equal to C. For example, let's take, this is 1, we'll do the graph, okay? Let A be 1, B be 2, and C be 3. The first one, A, B. A is less than or equal to B. So, 1 is less than 2. So, A, B belongs to R. Now, B, C. 2 is less than or equal to 3. But 2 is less than 3. So, B, C belongs to R. Checking for A, C. 1 is less than or equal to 3. Of course, 1 is less than 3. So, obviously, if A is less than or equal to B and B is less than or equal to C, there is no doubt A will be less than or equal to C. Therefore, this implies that A is less than or equal to C. Therefore, A, C belongs to R. Hence, the relation is proved to be transitive. For any real number you may take, this will satisfy. This condition will satisfy. Okay. So now we have proved that this relation is reflexive and transitive, but not symmetric. That will be the final answer. Okay. So exercise 1.1, fifth sum. The fifth sum, what does it say? Check whether the relation R in R defined by R is equal to A comma B such that A is less than or equal to B cube is reflexive, symmetric or transitive. So they're telling us that set R is nothing but set of all real numbers. Okay, and relation R is defined on R on this set of all real numbers such that A is less than or equal to B cube. Now we are asked to check if this relation is reflexive or symmetric or transitive. Okay, you will start with reflexive. So we know the rule for any relation to be proved to be reflexive is for every A belonging to A, set A, ordered pair of the form A comma A should belong to R. This is the basic rule for any relation to be proved to be reflexive. Right? Now, let me say if A comma A belongs to R. If I take A comma A to be belonging to in the relation that is R, what does it imply? It implies that A is less than or equal to A cube. It implies that A is less than or equal to A cube. Okay. Now let A be. I am going to take A to be 1 by 2 in this case. 1 by 2 is of course a real number. So I will take A to be 1 by 2 and I will check for this relation. Okay, A cube is equal to 1 by 2 the whole cube is equal to 1 by 8. Now, since what have we found now? We have found A cube. We know A is 1 by 2. Is 1 by 2 less than or equal to 1 by 8? The answer is no. 1 by 2 is not, it is greater than 1 by 8. It is not less than or equal to 1 by 8. Now, since 1 by 2 is not less than or equal to 1 by 8, since 1 by 2 is not less than or equal to 1 by 8, we can say A comma A does not belong to R. Therefore, the relation is reflexive or not reflexive? Not reflexive. So how did we start? We started getting the rule that is for every A belonging to set A, ordered pair of the form A comma A should belong to R. Now, if A comma A belongs to R, it implies that A is less than or equal to A cube. Now, I am taking A to be 1 by 2. So, what is A cube? A cube is 1 by 2 the whole cube, that is 1 by 8. Now, here we find that 1 by 2 is not less than or equal to 1 by 8. That's what we know. Since 1 by 2 is not less than or equal to 1 by 8, A comma A does not belong to R. Therefore, this relation is not reflexive. Okay. Now, let's check for symmetric. We are done with reflexive. We will now check for symmetric. Okay. What is the rule for any relation to be symmetric? If A comma B belongs to R, then B comma A should belong to R. This is the general rule for any relation to be symmetric. Right? So, here I am going to assume that A is 1 and B is 2. Let A be 1 and B be 2. Of course, these two are real numbers. So, I am taking A to be 1 and B to be 2. I put number 2. Okay. So, if A comma B belongs to R, it implies that A is less than or equal to B cube. In this case, it implies that 1 is less than or equal to 2 cubes, right? It implies that 1 is less than or equal to A. This is true. This is true. Therefore, A comma B belongs to R. Okay. Now, because A comma B belongs to R, I am going to go checking for B comma A. Okay. If B comma A belongs to R, it implies that, what does it imply? It implies that B is less than or equal to A cube. It implies that B is less than or equal to A cube. Now this in turn implies that, what is B? 2. 2 is less than or equal to A cube. What is A? A is 1. 1 the whole cube. Okay. Which implies 2 is less than or equal to 1. Now this is false. This is false. Therefore, B comma A does not belong to R. Therefore, the relation is not symmetric. Okay, so how did we start? We started writing the rule, that is, if A comma B belongs to R, then B comma A should belong to R. I took A to be 1 and B to be 2. In that case, I am checking for A comma B if it belongs in the relation. So if A comma B belongs to R, it implies that A is less than or equal to B cube. That is, 1 is less than or equal to 2 cube. That is, 1 is less than or equal to 8. This is true. 1 is less than 8. Agreed. This is true. So therefore, A comma B belongs to R. If B comma A should belong to R, it will imply that B is less than or equal to A cube. Here B is 2 and A is 1. So 2 is less than or equal to 1 cube, that is 1. So 2 is less than 1, that is 2 is less than or equal to 1. This is a false statement. 2 is greater than 1. This is false. Okay. You can say, right, this is false because 2 is greater than 1. You can say that way. Therefore, B comma A cannot belong to the relation R. Hence, this relation is not symmetric. Okay. Now let's check for transitive. We are done with reflexive and symmetric. So we will now move on to checking for transitive. That is, if, what is the rule? The rule states that if A comma B and B comma C belong to R, then ordered pair of the form A comma C should belong to R. This is the rule for any relation to be proved to be transitive. Okay. Now, let's go to the rough page. Let's do a small workout. Okay. A, B, C, A is less than or equal to B cube, B is less than or equal to C cube, and A is less than or equal to C cube. The conditions for relation, and these are the elements A, B, and C. Now let's take A to be 1. Let's do a simple guessing. A is 1, B is 1, C is 3. Okay. If A is 1 and B is 2, what will be A? What if let's check if A comma B lies in R. Okay, first we will take A and B and check for the relation, that is A is less than or equal to B cube. Of course, 1 is less than or equal to 2 the whole cube. 1 is less than 8, right? So this is true. Let's check for B comma C if it belongs to the relation. Here B is 2 and C is 3. So 2 comma 3. The condition for relation is B is less than or equal to C cube, that is 2 is less than or equal to 3 cube. 3 cube is 27. Of course, 2 is less than 27. So this is also true. Now we have found that A comma B and B comma C lie in the relation. Let's check for A comma C, that is 1 comma 3. 1 comma 3. Of course, 1 is going to be less than 3 cube. Less than or equal to 3 cube. So 3 cube is 27. 1 is less than 27. So even that is true. Now for this set of elements, this relation might seem to be transitive, but that is not the case. We can't blindly say this is transitive because we check for just one possible combination. There are plenty of possible combinations because this is a common. This set is like infinite for all real numbers. So we have, after so many trial and errors, after so many checks, we found one set of plenty, but here we will take one set of combinations for A, B and C, okay, which proves that this relation is not transitive. Okay, now let A be 3, okay, and B be 3 by 2, and C be 6 by 5. A is 3, B is 3 by 2, and C is 6 by 5. Okay, for 3 and 3 by 2. Let's take A comma B and see if it belongs to the relation. We have to check for the condition for the relation is A has to be less than or equal to B cube. So 3 is less than or equal to 3 by 2 the whole cube. How do we check? 3 is less than or equal to 3 by 2 the whole cube. What is 3 by 2 the whole cube? 27 by 8. 3 cube is 27, 2 cube is 8. 27 by 8 is what? 27 by 8 is equal to 3.375. So 3 is less than or equal to 3.375 is what we get. Of course 3 is less than 3.375. So this is true, which means A comma B lies in the relation. Now we will check for B comma C. Okay, we will check for B comma C. B comma C. What is B and C? B is 3 by 2 and C is 6 by 5. Okay. Now, the point is 3 by 2 has to be less than or equal to 6 by 5, the whole cube. That is the point, isn't it? So, what is 3 by 2? 3 by 2 is nothing but 1.5. You can write 3 by 2 as 1.5. Has to be less than or equal to 6 by 5, the whole cube. What is 6 by 5, the whole cube? 6 cubes are 216. Okay. 5 cubes are 125. So you divide, what do you get? You get 125, 21.0677, 875, 35, 0. It goes on like that, okay? 1.72. We get 1.72. So 1.5 is less than or equal to 1.72. Of course, this is less than 1.72. So this relation also is true, which means B comma C lies in the relation R. Now that we have checked for A comma B and B comma C, we will move on to checking for A comma C. That is the final check. If A comma C belongs to R, then we are done with this, right? Now, A comma C. That is, A is 3 and B is 6 by 5. Sorry, C is 6 by 5. Okay. Now, we have to check if 3 is less than or equal to 6 by 5, the whole cube. Okay. Now, what is 6 by 5, the whole cube? We found 6 by 5, the whole cube to be 1.72 in the previous example. So, 3, which this implies that 3 is less than or equal to 1.72, which is going to be false. 3 is greater than 1.72. So, what do we conclude? We can conclude that finally, for this set of elements, this relation is not transitive. A comma C doesn't satisfy the condition. So, now let's start with an answer. Let A be equals 3, B equals 3 by 2, and C be equals 6 by 5. For these three elements, let's start checking the relation. Okay, if A comma B belongs to R, it implies that A is less than or equal to B cube, which implies that A3 is less than or equal to 3 by 2 the whole cube, which is 3 is less than or equal to 27 by 8, that is 3.375. 3.375. This is true. This is true. Therefore, A comma B belongs to R. This we are done. Moving on to B comma C. If B comma C belongs to R, it implies that what is B? 3 by 2 and C is 6 by 5. It implies that 3 by 2 is less than or equal to 6 by 5 the whole cube. Okay, which implies that 1.5 is less than or equal to 1.72. That's what we found. Okay, 1.5. This is true. Of course, 1.5 is less than 1.72. Therefore, B comma C belongs to R. Now that A comma B and B comma C belong to R, we will check for A comma C. Okay, if A comma C belongs to R, it implies that 3 is less than or equal to 6 by 5 the whole cube. Okay, we have found out 6 by 5 to be what? 1.72. 6 by 5 the whole cube is 1.72. But this is not true. 3 is not less than 1.72. This is not true because because 3 is greater than 1.72. Therefore, A comma C does not belong to R. Therefore, the relation is not transitive. The relation is not transitive. So, how did we start the rule? If A comma B and B comma C belong to R, then A comma C should belong to R. We went to the rough column, we did a few checks, and we found out that this set of elements give us the right answer. We took A to be 3, B is 3 by 2, and C is 6 by 5. If A comma B belongs to R, it implies that A is less than or equal to B cube as per the condition for the relation, which is 3 is less than or equal to 3 by 2 the whole cube. 3 by 2 the whole cube is nothing but 3.375. Of course, 3 is less than 3.375. Therefore, this is true. Therefore, A comma B will belong to R. Moving on. Checking for B comma C. If B comma C belongs to R, it implies that 3 by 2 is less than or equal to 6 by 5 the whole cube. 3 by 2 is nothing but 1.5. It is less than or equal to, we found this value to be 1.72. Of course, 1.5 is less than 1.72. This is also true. Therefore, B comma C belongs to R. Then, the final check, that is for A comma C. If A comma C belongs to R, it implies that 3 is less than or equal to 6 by 5 the whole cube. What is 6 by 5 the whole cube? We found out that to be 1.72. It implies that 3 is less than or equal to 1.72, but this is not true because 3 is greater than 1.72. Because 3 is greater than 1.72, this relation, this pair, A comma C, will not belong to the relation, does not belong to R. Therefore, the relation is not transitive. Understood? Okay. Exercise 1.1, 6 sum. Okay. Show that the relation R in the set 1, 2, 3. The set is given as 1, 2 and 3. Given by relation R is equal to 1, 2 and 2, 1 is symmetric but neither reflexive nor transitive. So this is very simple sum. They are giving you the set A to be 1, 2, 3. That's 3 elements, 1, 2 and 3. And the relation R, the values of R itself is given. That is, R has only 2 ordered pairs, that is 1, 2 and 2, 1. Depend on A. Now, if we are asked to prove that this relation is symmetric, but neither reflexive nor transitive. So, they are asking us to prove that this is symmetric, but not reflexive and not transitive. Let's start with reflexive. For reflexive, what is the condition? Again, the rule is for every element A belonging to the set A, ordered pair of the form A comma A should belong to R. This is the condition for any relation to be proved to be reflexive. Now, looking at the values of R, can we say that this is reflexive or not? Yes, we can say. And this is not reflexive. Because why? Because for all the elements of A, ordered pair of the form A comma A is not in R. We don't have 1 comma 1, we don't have 2 comma 2, and we don't have 3 comma 3. So how do we write? Since 1 comma 1, 2 comma 2 and 3 comma 3 are not present in R, since these three ordered pairs are not present in R, okay, the relation is not reflexive. So such a simple conclusion. Okay, understood? Now let's check for symmetry. We're done with reflexive. Let's check for symmetry. Okay, what is the rule for a relation to be symmetric? If A comma B belongs to R, then ordered pair of the form B comma A should belong to R. This is the rule for any relation to be proved to be symmetric. Okay, now looking at this relation, you can say that let's take the first pair, that is 1 comma 2, A comma B. For A comma B, B comma A is present. So this relation is symmetric. Okay, how do you write? For 1 comma 2 belonging to R, 2 comma 1, ordered pair of the form 2 comma 1 is also present in R. Okay, therefore the relation is symmetric. Very simple, right? Yeah, easily proved. Okay, now let's check for transitive. We are done with reflexive and symmetric, and we are moving on to transitive. What is the rule? We start by writing the rule always. If A comma B and B comma C belong to R, then what? A comma C should belong to R. This is the rule for any relation to be proved to be transitive. Right? Looking at the values of R, take the first pair, 1 comma 2. If that is A comma B, do we have B comma C in the relation? Yes. What is B comma C? 2 comma 1. Now, here, some of us may have the doubt. Sir, this is A comma B, okay. This is B comma A, na? How come you are saying it's B comma C? Some of us may have this doubt. So let's clarify it right now. For, if I am telling you that A comma B and B comma C, then that means any element comma B and B comma any element. This any element belonging to set A can be different values or can be the same values as in this case. You don't have to worry about this part. This part is all that matters. Ending in 2 and beginning in 2. This is what we need to check for. This can be the same or different. Still it is A comma B and B comma C only. Okay. So in this case, we have A comma B, we have B comma C. Do we have A comma C? Do we have 1 comma 1? No. There is no 1 comma 1, so this relation is not transitive. How do you write? For 1 comma 2 and 2 comma 1 belonging to R, 1 comma 1 is not present in R. 1 comma 1 is not present in R. Therefore, the relation is not transitive. So we have proved. Now what we have done, we have proved that this relation is only symmetric but neither reflexive nor transitive. Okay.